This conference will now be recorded.
So very good evening, students. We are discussing questions on interference from wave optics. So the questions we are taking up for discussion over here is from IIT JEE mains paper. Just a minute. So today we have pick up some 6 problems, 5-6 problems. So we'll try to solve those. So from all optics, there will be always some question because there are 3 important part here: interference, diffraction, and polarization. So interference itself, it is a like one big thing from where many questions can be asked. So we'll first pick up almost all the questions from JEE papers, past few years JEE papers on this interference. Then we will similarly revise for or discuss questions for diffraction and polarization also. Okay, so let us see this question. In a double slit experiment, that means you can just think Young's double slit experiment. Okay, when a thin film of thickness t having refractive index mu is introduced in front of one of the slit, the maximum at the center of the fringe pattern shifts by one fringe width. The value of T or thickness of the film is whether it is 2 lambda by mu minus 1 or lambda by 2 into mu minus 1, etc. So you have to find out the answer for this. So you look, if I think this is a screen, this is the screen, and I have 2 slits over here. Okay, and there is interference happening somewhere here. Suppose at this point light waves are coming from this 2 slits and interfering at this particular point on the screen P. Okay, so look here, if I introduce, suppose I am introducing a thin film of thickness T, then the central fringe pattern itself will shift by one fringe width. Okay, that means one order shift will be there. Okay, suppose there were central fringe here, so now one order, so by pattern will be shifted by one fringe width. That means one order shift will be there. So if there were first order here earlier, and central pattern was here, now what will happen, this first order will come here, central pattern will go here, because this will be central pattern. Okay, and this will be first order pattern and this will be second order pattern. So one order shift will be there. So you know how to solve this kind of problem. There are actually many problems I was seeing. In fact, we have 2 problems depending on this concept. See, whenever this kind of problem is there, you see, because of this particular film inserted into one path of the interfering waves, it will actually introduce an extra path length. Okay, so what will be the path difference in that case? So path difference will be mu minus 1 into t. So this will be the path difference. Now, okay, if this is the case, so t is the thickness, mu is the refractive index of this transparent sheet or film. So this will be the path difference. Now this path difference, since this particular fringe gets shifted, central pattern get shifted by one order, so I can write, actually in general we can write n lambda. Okay, n lambda, but since it is shifted, getting shifted by only one order, sometime it will be written as by fringe width one. Here it is actually one fringe width, it is written, that means it is shifted by one order. Okay, so look here, I can write this is equal to lambda. Okay, and this is equal to lambda. Okay, therefore thickness will be t is equal to lambda by mu minus 1. So this will be, this C will be the answer for this question. So the main point you should remember is this: the path difference after inserting the plate or thin film. Okay, now we will pick up related to this problem itself. Let us see here. So the figure shows a, here it is, Young's double slit experimental setup. You can see that it is observed that when a thin transparent sheet of thickness d and refractiveness mu is put in front of one of the slit, the central maxima gets shifted by a distance equal to n fringe width. Okay, n fringe width. Okay, n fringe width. If the wavelength of the light is lambda, then what is the t? See this, sometime we have to see how the answer options are given. Depending on that, we have to write this particular thing, like mu minus 1 into t. This whether I should write. So see here, you have to write n into beta. Okay, n into beta. Beta means n times the fringe width. Okay, so n beta, this will answer your question. So this is, see, this is small d is equal to a here. Then I can write this n, and beta is the fringe width, so beta d lambda by a, d lambda by a, because this is fringe width is a. Okay, so then you will get this is mu minus 1 down, mu minus 1. So what you get actually, n d caps lambda, caps d lambda by a into mu minus 1. So this is the answer for this question. Okay, so we have got n d lambda by a into mu minus 1. This is the answer. Now we'll move on to the next problem. So this is Young's double slit experiment. Say in the Young's double slit experiment, the slit widths are at the ratio of 9:1. 9:1. The ratio of intensity is maxima and minima are. Let me check whether it was 9:1. This let us take this according to these options. Let us take this as 4:1, not 9:1. This is 4:1. Anyway, whatever you take, you will be able to solve the problem. But in the original problem, it is 9:1 according to this options. Otherwise, options will not match with the answer itself. Okay, so let us take this as 4:1. So slit widths are in the ratio 4:1. The ratio of the intensities as the maxima and minima will be what? So this I have already discussed once. See, intensities are actually directly proportional to the slit width. Okay, it is directly proportional to the slit width. Then what I can write is that intensity, suppose it is some 4x, okay, 4x, and intensity for the other one is some x. I can just take it. Okay, so since they are directly proportional to the slit width, now we know maximum intensity occurs where in maximum intensity occurs. What happens? This is the formula for maximum intensity. So look here, I1 is 4x and I2 is 4, only x. For the sake of calculation, we can just omit this common factor x because there is root. It will be difficult for us to solve. Let us take this as 4:1 means let us take this as 4 and 1. There will be a common factor anyway. If you take the ratio, that will go away. I would have taken x square otherwise. So let me take then x square, 4x square and this x square alone. So then it will not create a trouble. Okay. So here then we can write 4x square means 2x plus this is x square means x. So it will be this. So this will give you actually 9x square, sorry, 9x square. Now similarly, we can find out minimum intensity by writing I1 minus square root of I2 whole square. And this, you know what you will get from here. So here you'll get 2x anyway, it is the same thing, 2x minus x whole square. So you'll get x square. Okay. Then what you are getting? I max is to I min is equal to 9x square by x square, that is 9 over 1. Okay, so it is 9:1. All right, so this is the answer for this question. Now we'll move on to the next problem. So in a double slit experiment, at a certain point of the screen, the path difference between the two interfering wave is this. Okay, path difference between two interfering wave is given as 1/8 of the wavelength of a wavelength. The ratio of intensity of the light at that point to that at the central bright fringe. So you have to find out the ratio of intensity of particular point to the central point. Suppose it has density I naught. So what is this value? This is the question. So look, we have path difference delta x is equal to 1/8 into lambda. Okay, then what is the phase difference? We can easily get the phase difference. So the phase difference is equal to 2 pi by lambda into path difference del x. Okay, so 2 pi by lambda into lambda by 8. So you get pi by 4. Okay, you get pi by 4. Now what we know is that we know that I is equal to I naught. This is the intensity at any point. This is the intensity at the central point or central maxima. I0 cos square del phi by 2. Okay. Okay. So this is the thing. So this is the intensity at the central bright fringe, and this is cos square pi by 8. So this will be actually I0 into I0 means I max. So central the intensity of the central maxima. So we can just write it here that I intensity of any point to the intensity of the central point is obtained as cos square pi by 8. That is actually 0.923, something like this. And whole square of it. So this will be nearly equal to 0.85. Okay, so option D would be the correct answer for this question. So now we have got a question which we are now trying to, we'll just write the question first and then try to solve it. So these are all actually from JEE Mains paper 2019. So now this question is, two coherent sources produce waves. Two coherent sources produce waves. Produce waves of different intensities, of different intensities which interfere. interfere. After interference, the ratio of the maximum intensity to the minimum intensity, the ratio of, I'm writing in short, ratio of I max to the I mean is 16. The intensity of the waves. Now you have to find out the intensity of the waves. Intensities of the waves are in the ratio options are given, and the ratios are like 16.9, sorry, 16 is to 9, 16 is to 9. Then option B is 5 is to 3, 5 is option C is 25 is to 9, and D, option D is 4 is to, okay, these are the options given here. So two coherent sources produce waves of different intensities which interfere. After interference, the ratio of maximum intensity to the minimum intensity is 16. Okay, see, this is very simple problem. I'm directly going to the answer part itself. How to do? We have this formula that I max is equal to I root over I of 1 plus root over I2 whole square, and I mean is I1 minus square root of I1 minus square root of I2 whole square is the intensity. So these are the intensity expressions. So what is given is this I max by I mean is given as 16 is to 1. Okay, now then what we can write, we can write I1 so we can write this whole square terms. I can just, okay, let me for the timing write this whole square was there are 16 here. So now I'm just making them just without whole square, and this is equal to 4. Okay, now what we can do is we can just divide I1 root of square root of I1 by square root of I2 both side in the numerator and denominator. This is minus 1, this is 4 all alone. See, now what we can do, just multiply both side see we get root over square root by 1, square root by 2, plus 1 is equal to 4 into this. So we get actually 3 into square root of I1 by I2 is equal to 5. Then if we get this 5, then square root of I1 by I2 is 5 by 3. Then if we want to get what is I1 by I2, that will be equal to square of this term, right? So I1 by I2 is equal to 5 by 3. This is square. I'm sorry, this is not 9, this is square. Then I1 by I2 ratio will be 25 by 9. Okay, so look here, 25 by 9. This option will be the correct option for this question. Okay, so there are many such problems. We can just pick up one more maybe. There is a problem in, okay, let me just get this problem. This is actually from 2019 again, but this is a problem where we need little bit of diffraction knowledge also. So let us just go ahead with that. So this is also IIT JEE main problem number 2019. Okay, so the problem, let us say this is problem 6. The problem is that in a double slit experiment, in a double slit experiment, green light wavelength is given in bracket, that is 5033, sorry, 5303 angstrom, falls on a double slit, falls on a double slit having a separation of 19.44 micrometer and width width of 4.05 micrometer. The number of bright fringes, question is the number of bright fringes between the first and second diffraction minima. Between the first and the second diffraction minima. Second diffraction minima. Minima is, so between first bright and second bright, the number of bright fringes, there will be how many number of interference fringes, that is what is the question. Okay, the options are: A is called 5 interference bright interference fringes, there are 10, 9, 5, 10, 9, and the option D is 4. So now you have to solve this question. So how to solve this kind of problem? So in this case, you look, the wavelength of the green light is given, the lambda is given, then the distance between the two slits are given, that is D is given. Now width of the single slit is also given, that is 4.05 micrometer. So then we can actually able to get the angular width of the first and second diffraction minima. How do we get? So let us say, okay, let me just go to the next page itself. So here D is given as 19.44 micrometer, A is given as 4.05 micrometer, now wavelength is also given 5303 angstrom. So here we know the angular width between first and second diffraction So what is the width? Width actually given by lambda by A. This is for simplest one. Okay. So once I get that, this theta prime, let us say this is theta prime is equal to this. Now number of fringe width will be actually number of fringes between first and second will be obtained by the ratio, sorry, theta by theta prime. Angular width of the bright fringes are this actually. At this angular separation, angular width of this the fringes between first and second diffraction is given by this, and this is the thickness of the bright interference fringe. Okay, each fringe. Then what will be this? So we have got lambda by A, lambda by D. So lambda gets cancelled. Here you will get D by A ultimately, and D is how much? And A is already given, that is so this will be, after calculating, we'll be able to get almost a decimal number, 4.821. We have to see the answers. Now this 4.81 is what? So if this is the case, number of fringes we have to calculate, then n has to be so this is the fringe width, but it is not possible to have, so therefore it will be in integer number. So 5 will be the number of bright fringes in between the first and second interference fringes. Sorry, yes, first and second diffraction minima. Okay, so for diffraction minima we know lambda by A is equal to this theta, and similarly we can write for theta prime. Okay, so with this we get to see that the number of fringes you get here is 4.8 something. So it is actually, you have to take a positive, so this number has to get some whole number, okay, or integer number. So that's why it will be compensated, compared to 5. Okay, so how many bright fringes will be seen? 5 bright fringes will be seen. Okay, all right, so we'll stop it here for today. Next day we'll pick up again few more problems. In fact, there are many problems on this wave optics part. We will try to solve all of them almost slowly. So thank you for your patience. Bye for today.